All right, good time of day, everyone, and welcome to this new edition of the MLIR meeting. This week we don't have a presentation, but we thought we would talk about one of the topics we discussed on this course, which is on the topic of tiling loops in the tensor domain. And Mahesh had some thoughts on this. So Mahesh?
Yeah. So just to give some background, just so that let me pull up this post insert. So I posted something based on discussions I've been having with mostly Nicholas and a few other folks about how to represent tiling on tensors and parallelism of the tile loops in that context. So to give some background on that, if you start with the linear job and you tile it, the linear job works on tensors. If you tile it, uh, it and you can also during the tiling transformation also do a distribution of that loop, which does a block cyclic distribution of it. And there are various options that allow you to control the distribution so that you provide the processor ID and number of process to do the block cyclic distribution. So that leads to some representational issues. Uh,
Can you
let me
zoom a little
start.
bit, maybe?
Yeah, I can, but let me start with let me start with some background on like loops on tensors in general for people who might not have looked at this before. So this is the SCF4. Uh, this is, yeah, mostly SPMD. It's hard to kind of differentiate between the different flavors of this, but it's the same code. I think that's actually one of the problems. So maybe we can defer. So there's a question on chat saying that is this an SPMD context or MPMD context? And I think that might be one of the issues as well, because there's no easy way to distinguish between the two. So, let's step back a bit and just look at the loop construct on tensors. So here, the loop is returning a tensor value. I don't have the tensor types on this slide for whatever reason. So there's an init value that comes in as the iter args to the loop. That's the, if you can see, percentage arg1. Init comes from outside the loop. There's some computation, and then the loop yields a value. And this effectively forwards the value from one iteration to the next iteration. So percentage arg1 takes the value that is yielded here, and the yield of the last iteration is the result. So that's how loops work on tensors. So in the context of tiling in lineage, if you let me zoom in a bit. Let's say you start with a simple 1D generic operation I have here. Is that clear enough? To me, it's not looking very clear, but I don't know if it's clear for everyone.
It's readable, or just
Yeah.
for me, it seems good.
Okay, cool. So if you start with this generic op and you tile it on tensors, you basically get the so inside the lineage operation, you have an input, and then you have an out, which represents kind of the initial value of the result. So you take an input, you have an initial value, you compute, and you get the result of the operation. And when you tile it, the initial value becomes the value, which is the init value of the loop. That goes into the loop body. There's a computation, and that value is yielded. The value yielded is to say it goes back into arg0 for the next iteration, and then you do the computation, and percentage 3 is the result. So it uses the same SCF4 construct. The additional thing to track here is that this is actually using a destructive update. And what I mean by that is each iteration of this loop is computing a tile of the result tensor. And the way this is modeled is that you extract a tile of the arg0, that's the current value of that, that's the input to this loop body. You do the computation. So this is a tiled version of the same lineage generic op. You take the result tile value, and then you insert it back into the same same arg0 that you got at the beginning of the loop, and then you yield the full tensor. So each tensor, each iteration of this loop is computing one tile of the final result, inserting it into the current value of the full tensor and yielding the full tensor. So this is the destructive update pattern, because at every iteration, you're creating what portion of the specified styling. So that is done in C++. So this is the initial code, and then you can use the tiling transformation that exists in Lineage to get this code. So the tile, is that the question you have, Sriram? Or is
Good
that
question.
So I'm trying to see, if I look at the code that you're showing, I want to see, this is the tiling specification in this code, right? I mean, I see something else drives the determination of the tiling, but which part of this code says this is the tiling, and whether it's rectangular tiling or hexagonal tiling or whatever, right? I'm trying to understand. Just looking at this code, how do I know what it's doing in terms of tiling?
Yeah, so this is just like rectangular tiling. Lineage mostly implements rectangular tiling because it's like a structured op computation. So the op shape and the iteration domain are kind of linked.
Okay.
Yeah, that's what like I was saying. So the way this is represents a tile computation is because you have this tensor extract slice, which, if you're familiar with the syntax, it's basically offset and size. Okay, so my offset value is wrong here. It should be percentage ID0. Right. So this is extracting a tile of the input and a tile of the initial value, and it's a tile because of the offset and the size. So the size is again the tile size, which is computed as a minimum of the actual tile size used, and so it's basically accounting for partial tiles. So that is your tile size, and then you extract a slice and you compute on that. Where was I? Yeah. So the issue comes with representing parallelism, because if you look at the original op specification, this loop is actually parallel. So all the tiles are independent. Each iteration of this loop is computing a non-overlapping slice of the final result. But due to the tensor representation and the way destructive updates work, this information is lost. And the question that I had was, how do we represent tiling on tensors while maintaining the parallel semantics? So there are a few options. And that's why I just kind of thought I can go into more in that, but I think might be worth pausing here for a bit to see if there's any more questions about what the problem statement is.
Yeah, I'll be that guy and say, what is exactly lost that you're concerned about being lost? Which semantics are lost?
So if you look at this loop here, in the SCF4, if you just follow the pure dependencies, each iteration of the loop is computing a new value and it is being passed to the next iteration of the loop. So this loop has a dependence. Because of the destructive update pattern, because each iteration is computing a tile, inserting it into the current value of the result and returning that to the next iteration. And that's purely a representational problem, because if you write the same loop on like a memref type, then you could read a slice. It's not reading a slice, you're not loading. When you take a slice in the memref world, the memref.subview, you just get a pointer into the subview, and then you can basically just remodify the subview itself. And you can also use SCF parallel or whatever to say that this loop is still parallel. So you can maintain that semantics, and that works on buffers. But when it comes to tensors, because of the destructive update pattern, you cannot make. There is actually a dependence that is introduced, and you need to respect that.
So let me jump in here, because there's a few. I think there's a few things that are not exactly like that. So basically, what this is right now, this particular code is the original op that has been tiled sequentially. There's no parallelism here. You tiled
this one is not. Yes,
yeah.
This one is not.
Now the question is, how do we make or how do we tile in a parallel fashion? How do we get parallel semantics after tiling? And so there's multiple ways to do that. But one way that does not work is programming that sequential for loop as an SPMD loop, meaning essentially adding indices corresponding to thread ID, etc. And so if we do that, the problem that we actually have is that each thread is going to race, update a local portion, and then try to write back or return the whole tensor. So everyone is going to race, returning the whole tensor. And that's actually the problem. Like there is a race and only one thread usually has its result propagated. So that's something we identified, I think, back in November last year.
Yeah, something like
1 year ago, actually.
Yeah.
And so a bunch of work went into how, like, what does it mean concretely? How do we model this, et cetera, et cetera. And so the problem is that really the tensor return value doesn't allow you to just have parallel semantics with, I would say, quote unquote, easily. When you're in bufferland, you don't have this problem because you can have many threads updating through the same pointer, and they're not going to clobber each other unless they actually write on the same portion. So that's really where the race is coming from. So I guess maybe, is that clear enough? Is that accurate enough why SCF4 plus tensors cannot just be distributed, basically?
But doesn't it go back to you cannot distribute it, and if you try to take this loop and try to distribute it, it races because that loop is actually sequential in TensorFlow.
Yes, but we do. I mean, maybe the other. I guess the other way to phrase it is to say this is a sequential loop, and it's a sequential loop. That's it.
Yeah, but there is sequential. Sorry, I didn't mean to interrupt. It's sequential because of the tensor representation. The computation itself is parallel.
No, it's sequential because it's a sequential construct.
Yeah.
Now, we could use exactly the same construct and add attributes or other information to say it's now has parallel semantics, but the parallel semantics is still, it's a fake thing, right? It's not materialized until you actually decompose your code on multiple threads, until each thread has a program counter, et cetera, et cetera. Right?
I think there's something though that Mahesh was trying to say that resonates with me, and maybe Mahesh, correct me if it's not what you had in mind, but you can have a SCF4 loop without iterarg, right? SCF4 would still be a sequential loop, but if you write it on memref, you could say that fundamentally there are no dependencies between iteration in SSA or conceptually or whatever, right? It is a parallel loop, even if it's an SCF4, or it could be scheduled in parallel. Whereas in the tensor domain here, this loop that Mahesh brought is not parallel in the sense that there are dependencies across iteration, and we don't have a way representationally to break those dependencies. You could say that I know that after bufferization, there won't be anything, and I will have a pointer per slice, and I can run concurrently. But you cannot really model this in the value domain. It's just a mental representation in your head that when you have side effects, you could schedule it in parallel. And
I don't think there's so I understand what you want to say, but I think you still when you said you can have this loop on memrefs and now say magically that it's parallel until it's actually materialized with thread IDs or OMP num threads or whatever, it's still sequential.
Yeah, but you can slap. It's like in C++, right? Or in C, you can write a for loop and slap an open name, pragma OMP parallel for around it, right? In the sense that you can say as a programmer.
And you can do exactly the same thing with tensors.
Right, and so what I'm saying is that from my point of view, you cannot do that with this loop here, and the reason is that if you have two iteration, that runs in parallel, right? We're gonna have we're gonna insert basically the yield at the end doesn't have a semantic with OMP4 fundamentally, because there's no reduce. There's no way to combine the yielded value of each iteration in parallel. To me, that's the main thing.
I think that's a red herring, because until you actually have code that executes in parallel, meaning until your OpenMP pragma actually turns into thread ID something and actually executes on two processors with two program counters, right, going through the runtime, etc., you're still just slapping an attribute on your loop, and you can very well do that at this level.
Let me, I mean, what both Mahesh and Mehdi are saying is that since you have these data flow constraints, since you are actually passing the result of the yield to the next iteration, the attribute is just not correct. You cannot slap it or just add an attribute OMP parallel or anything on the loop without violating SSA. It's not correct.
You can add any attribute you want. I mean, I don't see.
I guess no.
Attributes.
Sure, Nicholas. I guess the question is, what is the semantic? Like, now we have to describe it. And hearing you talking, I started imagining, like, let's try to describe it. What happens? What do you say is the guarantee, assuming that you have this attribute that says the loops are parallel? What do you say is the semantic of reading values from the tensor at each iteration now? Because you're supposed to, from the definition of SCF4, you're supposed to get the tensor value produced by the previous iteration. Now it's no longer the case because they run in parallel, right? So we have to be able to say, and that's the weird thing in Mahesh's proposal. It's like, now we have to be able to say.
They are not running parallel. Until thread IDs are materialized, nothing is running parallel.
No, I mean, I think I think we're not talking about the same level of analysis. To me, semantically, as soon as you add pragma or MP parallel 4 on a loop, we have to be able to reason about it as if it's running in parallel. Like, I should be able to write an IR interpreter that would now run in parallel in the value domain.
So, but what Nicola is saying is that you could have an attribute that doesn't have these semantics. That's just, think of it as a marker that will be processed later, and maybe pending some further downstream analysis to actually check that the dependence has disappeared. And then you can turn it later downstream as an OpenMP.
I'm not even saying that. What I'm saying is that you can take any loop and put a pragma OMP parallel around it, and it may or may not be correct depending on what you want to do, but it will not execute in parallel until it's translated into a loop that has thread ID XYZ.
But if it's not correct, then it violates the IR constraints. It has to be semantically correct.
You can put a pragma OpenMP parallel around anything. Loop.
Like, constructively, there's something where I disagree with you, is that constructively we have an SSA dependency, cross-iteration SSA dependency.
Yes.
Right. So constructively, you cannot explain to me what the meaning of the pragma MP parallel 4 is. Whereas in any C loop where you add a pragma MP parallel, you can always constructively, like structurally, map it to a parallel construct.
I mean, just to be clear, if I may interject, I think essentially, I mean, parallel, maybe, we could use a different word, right? Let's say they are concurrent. So all an OpenMP pragma for parallel 4 says is that different iterations are concurrent. It doesn't say anything about how it should be executed, right? That's a separate thing. We have one thread, it's sequential, multiple threads is parallel, but the key is we are asserting that the different iterations are concurrent. So the question here is, when we add an attribute, are we asserting a property, a semantics with that attribute? Or we are saying, well, I'm just throwing some information for me to use later, right? More like a way to memorize something with the AST construct that we have.
Right.
That, I guess, seems to be the question.
That I think is a very good point. And I would say, in the same way as for OpenMP, you are asserting that these things are concurrent. However, you cannot materialize it until you run buffers, because there's a race coming from the SSA values. You just cannot materialize it. It doesn't mean that it doesn't have the property. It just means that that property cannot be materialized until some point.
Right, but the property should be able to be expressed in terms of the SSA value. I think what I'm missing here is that you need to be able to explain semantically what it means for this attribute to be valid, like for someone to put it there. And for example, it could mean that you guarantee that every iteration will read different value from the iterarg. right? Will read a different subset. There cannot be an overlap in the subset that is read from the iter arg between values, for example. Because
I think the difference
and similarly
between,
for the produced.
Yeah, I think the difference, at least from how I hear, maybe you, Nicholas, you say is one semantics is to say that this attribute asserts that these are concurrent. The other way of thinking about it is that this attribute is specified by the user to say, you better make these loops concurrent at some point in a transformation, otherwise you fail, right? If the semantics is to tell the infrastructure to make these loops parallel at some point, downstream, then we are more now enforcing a transformation rule rather than specifying a property. And in that sense, it'll be different from open and parallel for, right?
Yeah, absolutely.
I guess the question is, does it have to run in parallel, or may it run in parallel? And may run in parallel may be very well specified also in OpenMP and have races, right? So
note that my pushback on what you're saying here is not based on races. Right. It's based on an SSA, a direct SSA dependency. It's like if you put two operation, like a chain of SSA value, producer, consumer, and you tell me those are all in parallel. But now when I hold a use of the last SSA value from the chain, you cannot tell me all of this value has been produced by all of those in parallel. There is a chain of dependency at the SSA level.
But what theorem is heading to, it would be compatible with that. It's not saying it's,
yes.
The goal is to make it concurrent at some point, basically. That's some of, it's a kind of odd way of designing the flow, yes, but I think that would make sense semantically. Yeah.
So the part that is
that becoming parallel is not possible, as far as I know, while we're still in TensorNet.
Unless we listen to Mahesh. If we listen to Mahesh a bit more, then we might actually have a solution in TensorNet.
No, it's not my solution. It's basically what. So this is the thing. So following the discussion that happened so far, to me the difference is you can say that this is concurrent. Let me use that terminology. I think that makes sense. You can say that the iterations of this loop are concurrent, but to materialize that concurrency later in the flow, there are two things that you have to recognize. There's also an implicit contract that you can recognize the destructive update pattern to undo it at a later stage of time. And that is not very easy to recognize because you have to look at the tensor extract slice and then the tensor insert slice, match that is the iter args, and then kind of undo that destructive update. Is that otherwise you cannot actually materialize that concurrency? Is that fair to say? That you have to recognize a lot to kind of undo the dependency that is there at the SSA value level.
So here I think you're talking about the correctness of the concurrent semantics with respect to some program execution, and I think that it's a connected point, but it's a separate point. Right, so we can take a loop, we can run it in parallel, and we can generate wrong code, or like parallelizing a loop may produce incorrect results. That's a fact of it.
That's true. Yeah, I think you're right there. I think that the difficulty for me is that we are relying on this destructive update pattern, which is encoded in the IR using like a complex sequence of operations, which is very hard to recognize. So later on in the pipeline, if you want to undo it, it's kind of like ninja tricks you need to do to undo it.
So I think you're talking about something else here, right? I think you're talking about the insert, extract operations, or more generally subset and subset insert type of operations.
Yes, to some extent, but it's not just that. It's also that on the different iterations of that loop, this combination of extract and insert slice are guaranteed to write to different points in the space. Like the tensor insert slice across iterations is always going to insert in non-overlapping domains.
Yes, but to have that information that the inserts and the extracts, etc., will not overlap. Let's say that's an information you're interested in. You can either write an analysis from this, which will then go into the same kind of discussion about, why do we have analysis on memory, etc., etc. Like it will be quite similar. Or you can produce it by construction from a parallel loop that is tiled, and now you have not lost the information. What happens here is that we lost the information.
Yes, and this information lost is kind of what I was trying also to Stefan, you want to quickly say what you have to say before you drop off?
Yeah, so I guess I guess my main question is, why do you have to tile this into an SCF4? Since it seems like if you tiled it into a lineage generic loop on the outer, then you have this implicit reduction of tensors that you want to express. And then the trick becomes, how do you take the original tensor and coerce it into a tensor of a different shape, which seems like a good logical operation that we should be supporting on tensors anyway.
Right. So the difficulty here, I guess there's multiple answers to that, but so the first point is lineal.generic does not support nesting, so you cannot have a generic within a generic. We can go into details about that, but that's why basically this work on lineage.tiled loop has been evolving. But more generally, the question of, can you rewrite 10 into 2 times 5? Yes, when things divide properly. As soon as things don't divide properly, a bunch of unpleasant things start to happen.
Mm-hmm. So isn't the fundamental question about how you handle the unpleasant things at the boundary? And
exactly. And the way it's currently handled is SCF4 plus other lineage operations.
Okay.
I would say the natural extension to what Maxime is suggesting is, yes, indeed, going from a tensor to a list, but it's to a list of tensors. So it would literally be from tensor of (F32) to tensor of 4 times tensor of (F32). And that is necessary because otherwise we do not have a way to say that each of these these things become ragged, right? At the boundary, they're ragged. They don't have the same size. And so they need multiple actual runtime value. Let's say if we represent them in a type, to say that, oh, the value here, the question mark, is actually a different runtime value each iteration.
Or maybe it's not, and you take care of the fact that you have to make some sort of policy decision up front in how you do that, like you're padding out the original tensor to make it a smidge bigger.
Exactly. Padding is the way out to avoid turning this one question mark into a list of question marks. So padding is one option to do that. And essentially, if you want to go from a lineal generic to a higher dimensional lineal generic that is tiled, in general, you need to do some type of padding, indeed, if you want to keep it closed under that. So either you can pad, or you can create a list, right? So tensor of 4 times tensor of question mark, or you can say, well, actually, I'm not going to create a list. I'm just going to iterate, and at each index variable of the SCF4, you actually get one element of the list. So you keep the same dimension, except at each iteration, you get a different value because you get a mean of something. Right, so these are the 3 ways that we've been wrestling with on how to represent this.
Right, but I guess it seems to me like the part of the solution to this is to bring that design decision more upfront, so that you can get to representations like lineage generic, where you have an implicitly parallel generic reduction kind of thing.
Yes.
And then worry about how you take the lineage generic and lower it to a sequential or an SPMD loop or something else after that, which is something that is sort of a separable concept.
Yeah, I fully agree with that. I would just say that the different seems that the natural way to get to that would be to have a nested tensor type. That would be the most natural way of going higher dimensional without loops. In the absence of that, We haven't found a better way.
Okay, cool. Thanks. Bye.
All right.
Sorry, now we cannot hear you, Mehdi.
You were unmuted just now, and there was some background noise, and then now you're muted.
I wanted to say maybe we should look at the question from some of the question from the chat. So Stefan went there. Maxim, I think Maxim was asking, have we looked into a representation that that would return a list of tensors? And I think what they have in mind was returning a list of, well, there would be one tensor per type. Maxim, I don't know if you want to present.
Yeah, I mean the discussion that you guys, you guys shouted me out like twice. That was basically what I was implying. Yeah, the discussion just you covered it. Yeah, I mean
Okay.
it seemed to me like a hack solution, but apparently you could. It seemed that at face value like, oh, this is a hacky solution to this problem. Hey, I'm going to write into a list of tensors rather than returning the entire tensor. But in order to be able to do that, I need to splat or split or whatever you want to call it into the list initially. So
Right.
anyway, you guys discussed it.
Yeah,
So
and reconcile. Okay.
if I can go on the list of tensors a little bit, to me that's only half the problem, because once you have the list, you also need to have the information of how you stitch together the elements of the list to get your full tensor eventually. And I don't think there's a good way of representing that either. I think that's the issue that comes up with the lineage style loop as well, because it kind of tries to do that where each iteration yields a slice, and then there is a way to say which slice it is yielding, and that representation is a bit tricky. I'm not sure there's a clear way to express how to stitch those tensors back.
Yes, I mean that's something that was suggested before, indeed, to have like ops with regions such that the special terminator stitches things together. This has also been considered, but it gets very messy very quickly. Like the reason we have these insert extract sites, that it's by far the best so far, but there is likely much better solution indeed if we go to a nicer type.
There was another remark on the chat from Eyal, who said, like in OpenMP, when there are dependencies and that must be broken for the loop to be parallel, you can specify the reduction clause, which is similar to accumulating tiles. And so maybe, I don't know if it's, because this is also my line of thinking, and I commented on the forum in this direction, I think, Mahesh. So we have a parallel for construct that supports a reduction clause, right? So I don't know if you want to show it and talk about that now.
Yeah, well, I didn't. Yeah, so that's one of the solutions, is to make SCF parallel work. I don't think I actually wrote. Yeah, Mehdi wrote it. So this is the representation with SCF for parallel with a region, which basically adds a reduction across the slices. This, I think the point that is a little bit not clear to me in terms of representation is it basically, again here with the slices, it has a better representation of the destructive update. You don't really have a destructive update and loop carry dependencies in the say value, but you still have the insert slice, and each iteration is yielding the whole tensor again, which is not what you would probably want to represent. You would really want to represent each iteration yielding a tile and a way to stitch together a tile. Because if you take it this way again, when you're trying to parallelize it, you have to know that actually this yield is not the whole tensor, but just a slice of the tensor. So that requires a little bit more analysis, but it is better than what was there before on the loop, but doesn't solve the problem the whole way.
I think it moved the problem to the reduce clause, right?
Yeah.
And maybe we can just spend some time on the difference with the previous representation in case it's not clear for everyone. So the operation now is s.parallel. It's no longer SCF4, so it doesn't have loop carry dependency. So there's not this iter arg argument that existed before. There is no value that is passed from one to another. So one of the important change, and because I copy pasted my code, there is the same error on the extract slice offset, but the extract slice now will extract a slice from not a loop carried value, but from always the value before the loop, right? Because the iterations are in parallel, so the SSA value you get at each iteration is the one before the loop executed. And then you compute exactly the same thing on the tile, but you have the reduction. And the reduction is an SCF reduce, which contains a region of itself. And you could think of it, one possible thing is to say that only this part of the code has to be sequential across each iteration, because this region will take two values, the values from the current iteration and the reduced value, which can be in any order of iteration. And it combines the two and updates and yield a new value. And so I think what you're saying, Mahesh, is that we still have the problem that here we have this implicit like cross iteration reduction that operates on full tensors and not on subtypes, right? I just hope it was useful to try to
yeah, no, that's
structure.
useful. I think that's a good, I think at this point I might be, let me just scroll down a bit on this part. So this, when we ran into this last year, when we were trying to get the lineage and tensors plumbed through an ERI, I still have the same, this I can correct, but yeah. What we did in ERI is we introduced two constructs. So it's the same loop, but now you have these two flow dispatch tensor load and flow dispatch tensor store. The flow is just a dialect. Flow dispatch, you can ignore it. Think of it as a tensor load or a tensor store, which is basically says that I'm going to read a tile of the tensor, and there is some background infrastructure which you don't need to specify that will give you the value of the tile. You do the compute on the tile. So here, if that's the percent 5, percent 6, you do the tile, you load it from some ABI or some data structure that is opaque to you at this point of time. You do the tile computation, and then you use the flow dispatch tensor store to say, take this tile and put it back into the original tensor using the offset and the sizes. So this kind of assumes that there's some infrastructure behind the scenes that gives you this tile and takes the tile and knows where to write it back based on the offset and size. And this solves the representation issue, because it kind of just says that, okay, I have some infrastructure that's going to give me this later on. You actually don't need any infrastructure, because when you go to memref and you actually bufferize this, you can basically just use a pointer offset and load it and store it. And the semantics is that if multiple iterations are loading and storing to overlapping tiles, then that's a race. And that is inherent race of the computation. So that solves the representation issue that to some extent, this works very well for us. In ERI, we use this, but there's nothing of this sort in core. So maybe the other option is maybe one of the things that already exists could be adapted to a computer.
Isn't it like the same as a memref semantic at this point?
What you load from is memref. So it gets into mixed territory now. It's not a pure tensor representation. You have a memref data structure. It's not a memref in ERI. It's like a different type. Which
Yeah.
That's a detail of ERI. But yeah, it is a mixed representation at this point. You know that you have a data structure that you can read, modify, write. But within the loop, we are still working on SSA values, except that you have these load store at the beginning and end of it. So
no, I think that what worries me is that it's much less opaque than you would like it to be. So compared to the tensor slice or tensor, like when you have just one operation to insert a slice, basically, you lose some opacity because you have this way to break the tensor into pieces and build it slice by slice. But it's much less than having some kind of random access load and store, even if you do preserve tensor semantics inside. So I would say that it solves the problem, but it decreases the amount of opacity you would like to preserve in TensorLand. And there are multiple objectives that may not be all equally important when you work on tensors. But so I don't think you break anything in terms of functional value semantics compared to what we have today. But you're losing on opacity, and that could be a problem.
Can you explain that a little bit more? I'm not sure I followed that.
So depending on you're assuming that somewhere there is an operation that can do this random access load and store, which depends on the storage format, which depends on how much information you have later on to lower the load and store to the proper accesses in memory. And it may very well be not even be local. It could be an RPC or whatever. So you don't know yet what the tensor is at that point. And so you're putting more pressure on the ability to lower it later.
That's true.
I hope you noticed it's no longer some other pressure you're putting here. Is like it's no longer in the value domain. Like this is a buffer that has been pre-bufferized. So you need also, if you had multiple loop in a function, you would need to pre-allocate buffers for all the values flowing across loops.
Correct, but assuming you want to unlock the problem with the spurious dependencies of the
Right.
current solution, you would also break out of the value domain anyway, like with reduce or anything. So I mean, we have already broken out of the value domain, I would say, to a large extent.
The reduce, the parallel with reduce?
Yes, I mean, it hides, it delays the dependencies to a reduce clause that gathers everything, but it's not. It's a black box, basically. It's a hack to capture that works. It preserves functional semantics, but I would say that the reduce solution is already losing some of the value semantics that you used to have, but that was sequential. It's okay. Functionally, it's fine. You're not breaking SSA properties. I agree with that.
I'm not talking about the SSA property. It's mostly the fact that here you need to allocate a buffer. Like if you were to do it upstream with MLIR, for example, you would need to do alloc and load store basically. Like what Mahesh is showing here is you read to allocate storage, and that becomes always a bit complex. Right?
When you lower reduce, you have to do it as well. But it's okay. Yeah.
Yes.
Right. That's basically what happens in ED. It is broken up. So this is at the point where you know that you are going to allocate. So this flow dispatch tensor effectively becomes a pointer and offset at some point of time.
I want to make sure you have time to discuss the tie loop proposal, but my impression is that we are mixing multiple levels of abstraction here, and definitely we want to remain at the higher structured op level. Like I think tie loop is one, although I don't like the name. And that we are missing that currently with lineage, and that doesn't mean that later in the lowering steps you don't want to get into this kind of loads and stores or reductions or whatever. I mean that it's a lower level abstraction, and Nicolas' hack, let's call it, may actually just work well at a lower level of abstraction for some flows, maybe not for others. But it's quite clear we are missing a level. Some expressiveness at the structured op level for mapping slices of tensors.
So let me propose one statement, and I'd like to see if people agree here. I would claim that none of what was presented and none of what we have in the IR anywhere is actually able to have parallel semantics on subset of tensor values or on subtensors. Like we do not have that abstraction anywhere in MLIR, I would claim.
Can you clarify what you mean by parallel semantic on subset of tensor? You mean parallel insert, or?
Yeah, I mean, and so that's a good question. It's like you have an SSA value. What does it mean to have multiple parallel things produce that value?
Right. What about tie loop that Mahesh didn't describe yet?
Tie loop is, I would say, is a way to encode this kind of Sorry, let me try to rephrase. Tie loop is a way to keep this kind of parallel bit until we have buffers, right? So it's specifically designed for that, even if it doesn't say so.
Should we present the tie loop construct?
I'll have to pull it up. Let me see if I can find it.
I mean, tie loop has a lot of history. Let's put it this way. It has tried to solve the nesting, but we found a certain number of problems, a certain number of inverse problems that were difficult. And at the same time, it also tried to solve the parallel plus tensors. And the result is something that works-ish, but still has many loose ends, I think.
What I don't like in tie loop is that it tries to behave as a loop, and while it should only be a map, really. But so it should not try to carry information along. But apart from that, and the name, I don't. But okay, I don't understand all the. I don't have all the background in mind that you're bringing up.
If you can zoom a bit, Maj.
Right. So this is the tile loop semantics, where it basically is similar to the SCF parallel in terms of representation, but apart from it has the same structure of a linear job. It has the ins and the outs, and then the iterators. It also has a representation for distribution, which is currently an attribute which doesn't really. There's another set of issues that I lay out in the post with respect to representing distribution. The attribute doesn't really work as well. It's kind of specific to CUDA to have it as, say, block X or something. But internally to the tile loop, you do an extract slice and you do an insert slice too, and you yield. But this is also still yielding the full tensor. So it doesn't really solve. So to me, I'm not sure it is actually differentiating with the SCF parallel sufficiently enough to solve the problem. It still has the same kind. It is a little bit better because it has. I'm not sure it's where it lies in terms of SCF parallel. It seems to have the same kind of semantics and same kind of issues, where it's again yielding the whole tensor instead of having a way to yield at the slice and independently construct the tensor. Maybe somebody who's more familiar with functional programming domains can even answer the question. Like, I'm not even sure you can represent parallelism in a reasonable way.
I'm a bit confused here. The tensor insert slice, is it inserting one slice, or is it like a generic map over all the slices?
It's inserting one slice into the tensor.
Then how can result be the full tensor?
Result is the full tensor. It's an insert. It's just like the insert slice.
It takes the full tensor, it inserts a sub tensor in it, and it returns the result. So it's similar to vector insert extract in LLVM.
Yeah, okay. No, but I think that's where it breaks the. You're trying to do too many things at the same time. Yeah, probably.
But so I would come back to that question, right? Is like, what do we know are the existing abstractions to produce a value from smaller values, to stitch them together, however you want to do it.
That's very parallel if it's fixed size.
Okay, concat.
But I know you don't want it. So
I mean, it's not that I don't want it. It's like we discussed it and we haven't found a good way to do it, right? Like I'm open to anything. It's just I haven't found anything, and so I haven't heard yet of something that would do the job. So a concat, for instance, one of the issues we've had is, well, what happens if it's an ND concat, right? Very quickly you go back to this subtensor insert extract type of semantics. Except instead of saying, well, let me just insert one, I'm going to stitch together a bunch of things in multi-dimensions. It becomes very complex very quickly. And there's been a few posts about that already, I think.
So I guess the closer we have is the SCF parallel with reduce. And something we mentioned was that the reduce is not parallel itself by nature. You have to prove that it can be done in parallel. But we could have a atomic update. We could have a SCF reduce insert slice or something like that, where you actually don't yield the full tensor at every iteration. You keep the SCF parallel, and then instead of a generic SCF reduce with a block, you can have like, you know, atomic insert slice, where
right. So maybe let me ask another question. Imagine there's no loops and no tensors, right? There's LLVM vectors. These are things, and they have very well understood insert and extract. You can only insert, extract one static element. Okay, now what does it mean to have two parallel flows that collaborate to create one vector value? How would we write that just without, no SCF, no tensor, nothing complicated that MLIR introduces, but just on those vectors? Is this something that is feasible? Is it something that is good to represent? Can it be done with values without going through memory, right? Like there's an easy way. You dump in memory, you just write and then you read. And you
with current vector instruction set, I don't know how to do that without a shuffle. It's not an insert. It's you're actually taking two things in parallel and merging them. And
exactly. But the shuffle itself is not parallel. It's a sequential.
It is. It's concat on steroids. It's just shuffling and concatenating. You're usually shuffling two things on vectors, but it's not like n elements. But shuffle is completely parallel. It's a symmetric.
I guess where I'm not sure I'm connected is that in my mind, imagine you have two threads, each getting the init value of a vector. Both of them want to update one element of that vector. The shuffle would be done by one of the two threads, not by the two in parallel. Right?
Oh, sorry, I was talking about instruction level parallelism here because we are discussing vectors.
Yeah, I mean, yes. Sorry, it's probably not a good analogy, but I don't have a better analogy to tensors than vectors because it's definitely not memrefs. So I guess maybe I'll try to restate the question, and maybe it's maybe it's not a good question at all. But imagine we have a vector value. We have two threads that get that vector value. Each of them wants to update one element in that value, and we want the final value to be agreed upon by the two threads.
It doesn't make sense. The threads have different registers. I mean, on CPUs at least.
So, I guess then the next question I have is: does it make more sense on tensors? So, if it doesn't make sense on vectors, does it make sense on tensors?
The vector way on tensors would be one instruction that's taken care of by one thread that joins symmetrically two half tensors or two slices.
But would that be run in parallel or sequentially?
In parallel, because it's just one operation, so it's in parallel with itself.
What?
It's just a map that concats everything. It's actually a reduce, but it's just a reduce that concats everything in as a black box. So that's why the reduce approach in the loop is not so bad, I think. But it hides many things. But if you want absolutely to be to work at the loop level, it's not bad at all.
Can I restate Nicholas' question, because I think I understand a little bit differently. So if you take the same example from earlier and you introduce the processor ID and number of processors, so now it's explicitly distributed. The question for me is all of the values, for example, percentage arg0 per thread, do they have their own copy of it, or are they working off some shared copy where they? And then if in theory it should be they're working off their own copy. But
in vectors, that would be the case. On vectors, that would be the case.
But then the question is, if all of them are working on their own copy, how do you merge the copies? That is still missing.
You need a black box that merges. Call it shuffle, reduce, whatever. But
exactly. Okay. And the claim is that black box cannot exist in parallel until it's on side effecting memory.
Yeah.
Like there's no magic. We cannot make that happen for now, at least.
It's okay. It's not the same level of abstraction. So you can at one level it's a magic thing. At lower level, it does what it does, like messaging or side effects or whatever.
So I heard at one level it's magic, and at the next level it does what it does, right?
But it has semantics. It hasn't. It's not really magic because it has precise semantics. It's just a reduce that concats. It's not very different from what you're proposing, except that it's more like preserving functional semantics as a reduction because it's a form of reduction, rather than marking things to be cleaned up later for parallelism, which I think works, but it's still a loop. So it's not very different from the flow you have in mind. But I didn't quite understand all the issues that the reduced solution had. But assuming these are minor, I think that
I think the red circle goes back to the same black boxing, right? Each iteration produces a tensor. Now you have to somehow merge those tensors, and then figuring out what exactly the semantics like that. Then that becomes a sequential step. And
then the reduce exactly, but the reduce clause or the reduce section has to take that op that concat op as an argument.
And that concat op is the one that has been notoriously difficult to create, at least in ND and with arbitrary shiftings. Right, so that's maybe one of the reasons that, I mean, I'm not versed enough in functional programming, but when you say map, it's usually a map of 1D thing. It's not very often that you say 3D map as one operator, right?
Sure, but
and map also doesn't allow you to do like tiles and like it basically the iteration space and the computation is the same. As many number of elements you return, each function returns, the map is n times that. So it's a very easy representation map. You can't have you don't have the problem of how do you stitch these tiles together, because there's only, like Nicholas said, it's a 1D thing. Depending on the return type of the function and the map domain, you get a data of that size. So.
Just I just noticed now we are out of time. But hey, I didn't think we would fill the hours with this discussion, but I think it was incredibly interesting to talk about this. And thank you, Albert, for joining. It was great to have your experience shared.
Mahesh pinged me on the discourse, but I didn't react, so that was my only choice.
All the people like Sriram, Maxim, and others who asked questions also, that was good to have, other perspective and thoughts. But yeah, we have to cut it there. We can always have a follow-up. We can continue discussing on discourse if people have thoughts about it, and take it from there. I don't know if it was helpful for you, Mahesh, at least.
I mean, we need to find a solution for this. So anything that gets along that path, start the discussion is actually what I was aiming for. So.
All right. Okay. Thanks, everyone. See you next time. If you want to have a similar topic of discussion, let me know, and we can always put it on schedule. Take care.
Thanks a lot.
Bye. Thank you.